Hello, my name is Alex Gonzalez, and I'm going to be working right now with a single list. I'm going to create operations such as create list, a free list to free the memory, add a node, and print the list, and let's see what else we can figure it out. So the first thing that I need to do is to create a structure that is going to be my node. And I'm going to add an integer that is going to be a val and struct node. Next, this is going to be my pointer to my next element in the list. I'm going to create list, which is going to need the struct node head. I'm going to use the address so it gets updated. Void free list struct node. Again, I'm going to use the address and print list. In this case, I'm not going to use the address, so let's start with these three. Oh, sorry. Let's start with this. Oh. Okay. To create my list, I'm going to need a struct node here. That is going to be my head create list. I'm going to send the head. Then I'm going to print the list. And I'm just going to send the head without the address, and then finally free list. That is going to include the head address. So the first operation, which is create list, is going to need it's going to need to evaluate. It's going to need to create a certain number of elements. For example, for int e equals to 0, em is less than 10, e plus plus. So I'm going to create 10 of this. So in order to create 10 of them, first I need a new node. Node asterisk new node equals to malloc size of the struct node. Now that I have it, it's important to initialize it immediately to null, because that's what this is going to be the terminator of our search. So I'm going to do pairs on the value. Next. Value. So the next is going to be terminator, and we need to initialize it to null. Now that we have a new node, we need to insert it to the list, and since we don't have any element, we need to verify that we don't have that precisely. So if the head is equal to null, then we're going to insert the first element, right? Which is the head is equal to the new node. And that's it. We have the first element inserted in the list, which is the head. And since we are sending the address, this modifies the original pointer variable that we have over here. So we have this here. So if it is not the first element, it means that we need to position an indexed equal to head an index variable till we reach the end of the list. So in this case, we're going to say index next. It's different than null. And then index next. That's it. Index equals. So what we're doing, or what I am doing here, is that I'm moving the index pointer since the beginning of the list to or till it reaches that the next element is null. In the first iteration, we define what's the head. The second iteration is going to tell us that the index, the new node that we're going to add, the index is going to stay in the head because the next element of head, the second iteration, is null. Which means the index is going to stay in the head position. So in the third iteration, what's going to happen is that this is going to come as the first a second iteration of the element. The first one is going to be the head, and then it's going to move to the next because the next is pointing to a second element, and the third iteration is going to tell us that there is nothing left in the next, which means it's a null. So the index is going to stay in the positions that we want to do. In any case, when you are coding, it's recommended to validate that on a conditional or some other places you don't have a pointer to null. If not, you're going to get a segmentation fault. Kind of here we have it controlled because we already initialized here and we are inside of a loop. But it's better, it's way better, and it's a good practice to have this condition here. You can just only say index or index not equal to null. Now that I have it there, I'm going to say that the index next it's equal to new node, and that's it. I have my index in the right place. And the new node is already pointing to null in its field next, so the next iteration is going to find this in the right way. So I think, if I'm not mistaken, everything is fine. The only thing that I want to do is to double check that when I'm moving over here, I don't reach the index to null. It's supposed to not get to null, but as I said, it's a good practice to say this. So if index, then we can use it as a pointer to structure, and then use the subfield as here. Now that's my create list. I'm gonna try it out in a second. Well, I can just build it and see what's going on here. Okay, it says that I don't have these two implemented, which is fine. I can just do it right now. Actually, they are over here. Okay, no errors. Let's execute single list, and there is a problem with the segmentation fault. So somewhere here during my creation of this, I'm having a problem, and let's try to figure it out. So the first iteration, the head is equal to new node, which is fine. And probably here I'm gonna have a mistake. Index next is not null, then this is validated, so the segmentation fault cannot come over here, only can come over here, but no, because I have it protected over here. I'm allocating here memory, and this should be not where I'm supposed to do things. I guess let me cancel out this one just to comment out if the error comes over here. Yeah, so I'm gonna go to this 4. Yeah, this 4 is causing me a problem. Index is not equal to null. Index in this field next. Index is equal index next. But index is equal to the head, which is fine. I'm validating that index is not null, which is fine. And I'm saying that I'm gonna move until the index, let me make a really quick graph for me. The index next is not equal to null. This means that if my index is over here, it's gonna pass, and that should be fine. But I'm supposed to protect my pointer by this validation. That is the first conditional that is evaluated in a for loop. So let's see, the first time I'm gonna have my head here. The second time, head is not gonna be null, it's gonna be in the index. My index is not gonna be null. Then index next is different to null. The second iteration, the answer is not different, it's null. So it goes out of the 4 and the index stays in the index. Ooh. Oh. Expected before 4. Okay, still. Okay, index is 1 when it's interesting because the val it says it's 1 when I'm doing only pairs. And the head should have 0 because the first iteration I is 0 and 0 times 2 is 0. Okay. first time. I'm not reaching the head, so if head is equal to null, the head is equal to new node, and I should print first, and I don't see it. I don't know why I'm not getting. Okay, this is weird. Yeah, I'm there. The first time head should be null. I'm guessing the problem is over here, and this is getting garbage because of the one. So I'm using a pointer head. If head is equal to null, let's see what's the value of head. Oh. The value of head is a place in memory that it doesn't seem to be valid, of course. Head is equal to null. Come on. That's the importance of having everything into null. So now I have a valid address. So it's time for me to get into this and have it there. First index 0, index nil. Okay, first gets in the right place, index okay. For index, if index is not, I don't need this anymore because I already got it. I already got the first is 0. And if not, then I'm gonna look into the index file. Index is equal to the head. And at that point, the head is valid. So I'm printing the number of times that I'm expecting a value of 0, which means this is not working as a new element, but index val. But the index is always the head, so this is not moving. Okay, so that's fine. I'm using the 0 every time, but I don't want that. I want to see the new node val, which is fine there. Now I don't want to see it there because this is anyway the place, right? But I want to see it here where it's already part of the list. That's where I want to see it. There we go. We have 0 to 16th. I'm missing one. And that's because missing one. Oh, I'm missing the current one. That's fine. We're gonna show it on the. We're gonna show it on the print. So let's implement the print. I'm not doing any free, so I'm just getting right now a lot of garbage in my memory. So struct node index equals to head for index not equal to null, index equals to index subfield next, and here I'm going to print the value of index val. So here it is. In the print I get it right. I'm not getting it in the index because the last element is going to be null, and that's fine. I mean, we don't need it here. What do we need is to free the list, and this is pretty much the same as this. When I need the index, when I need the head, but this time the head is this, so the head is going to be index equal to the index at some point. So while it's null, when it's not null, I'm going to free and free list. I'm going to say free list over here, and I'm going to say what I'm going to free, and then free the index. But I'm going to need another structure that is called TMP. TMP is equal to index, and then move the index to TMP. Perfect. And that way I'm going to free whatever is in this value, and then free the index, but I already had the index in the next. So index is going to be in the TMP. So if index at some point is null because the next was null, then that should work, and that's going to free the list from the memory and all the elements, and we're going to see that all of them are there. So in the print list, let's do something similar over there, like printf print list. And just to look at it better. Okay, so we're freeing 0, 4, 8, 12, 16. We're not freeing all of them. There is a mistake. We're moving the index here and not there. There we go. So we are freeing 0, 2, 6, 10. Okay, so now we have something clean. And that's how we create a random, kind of random list, or a list of 10 elements. This is how we free the list. We're using a temporal element to move the index in to the right place once it's free. Oh, something important that it's a best practice is when you are going to free something, in this case index, it's important to do the next element to point it to null. Why? Because it's going to be available memory for any other process that is going to come and use it. And if that process is a malicious process and it's identified as a structure that you were using for your list, and you have a pointer that's still valid to your list, then they can, I mean, the malicious process can hijack the memory and then access to your actual structure, and that's gonna be dangerous. So it's important when you are doing a free that any pointer that you have into your structure goes to null, and if possible, the value as well goes to something that doesn't have any meaning. I don't know. I'm probably saying that the value is going to be a pointer to another structure, or is going to be an array that still has some data. So it's better to make it clean and just add some data that doesn't make any problem, or doesn't have any security vulnerability that might be compromising your memory. So this is it. So just to test what we just did, yeah. So we're printing, and that's it. I'm going to remove the comment from here, from the first, and that's it. So let's add a new node. Add a new node to last, to the end. Add node. Let's just say add node. So we just need struct node. We are not going to change anything, so we're going to just send the head. Again, for another operation, let's add node in the middle. Let's say something similar. Let's have those here. The add node is kind of let's do a random value. Struct node, new node, struct equals to malloc size of struct node, and remember that it's convenient to have it to null. Then next, it's equal to null. Let's, in this case, in new node, let's just add a value of 5, just to do non-pairs, and then what I'm gonna do is to position it before or in between the 4 and 6. So for index val, oh, we don't have an index yet. Struct node index equals to head index file, it's less than file index, and of course index, we don't want to go to a segmentation full again, index is next, equal to index next, and then we have the index before, one position before the 6, because we are using the less than, the operator less than. So in the same level, we're gonna say, just to make sure, if index So this is kind of the operation that's going to be interesting because we have an index to the 5 element and we don't want to lose access to the next element. So the new node, the next is going to point to the index next, right? And even if it is the last element of the list, this is going to work because the index next is going to be it's going to be null. Yes, it's going to be null. Now, what we want to do is if the element is the current index to the node next now goes to the new node. Now, what happens if we are in the head position? If we're in the head position, the index is gonna stay in the same place. For example, actually, let's change this to add node, so we can do it properly. So we have a val value. So actually, this is the reverse. For or until the val is less than index val, then we're gonna move to the right index. Let's say that the first iteration we have a 0, right? If we have a 0, then it goes even before the index. So index, if it gets into the head, it's gonna stay in the head. So if we're staying in the head, then the value is 0 and the index val is 0. So let's say if val it's equal, if index is equal to the head, then it means we have the same value as the head, of course. And what we want to do is to set the new node before the first element of the head, which is new node next is equal to head, right? We're going to put it in the left side, which is fine. It's the same value. If we are thinking about a order list. Now, if we have this, then we need to move the head to the left, to the new node. It's equal to the new node, which means we do need to modify the head, which means we're free here. At node 5, I need to pass the address of the head, and that changed a little bit the game. So if it is not the head, value than the one in the head. Let's think if it is the last one. If let me draw it really quick. Yeah, so the else should work for cases where are kind of generic. For doesn't matter if it's in the middle of at the end of the list, and I think that's the way it should be, and we're gonna do it in two ways in a second. So, oops. So I'm gonna validate if there is an index, and if it's in the middle, the new node next is gonna be the one that is in the index next, and the one that points to the node that is pointing into the index, the next is gonna be the new node, and that's gonna be reorganized. If it is the last, let's say the last right now it's 18th. And the new node next is gonna be index next, which is null, which is fine. And the index next is gonna be, which is the last, is gonna be the new node, which is gonna make the new node the last, if that's the case for the new node having a value of 20, for example. And we're gonna do it here. So I'm gonna add one at the end. So actually, I'm right now doing both cases that I was planning to do. I was planning to do add node at the end and then just add node in the middle or so, but the middle doesn't mean anything. I'm just gonna add a node. Doesn't matter where it goes. I'm just gonna add a node. So yeah, let's try it out. Okay, 20. In the line 20, I have a problem with the head that says, so this is a value of this, okay? Index equal to head, okay? This is no longer a regular variable, what's the address? So, ta-da, no, I'm adding 2 elements to the beginning. That's not right. Am I not moving it this the right place? Okay, so first of all, let's see where am I adding those index. Oh, 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 oh. Index. Seems that like if index equals to head, seems like this is not moving. Index 05. It means that if it is the first time, the value it's 5. 5 is minor than 0 now. Oh. Oh. Okay, so I'm gonna move the index until val it's greater than the val. Means this index is gonna stay in the place where I'm looking for. If greater or equal, at least for the first element. Yeah. What is the print? Okay. Okay, there's a problem here. Okay. So I'm gonna if it's a 5 and the value is 4, yeah, passes. And then it's a 6, 5 versus 6. Index is going to stay in the place of this scenario. Probably this needs some special case. Let's see. Yeah. So okay, so it stays in the next element, and I don't want it in the next element. I want it before. Index is moving to the next one. If index is equal, index next. Okay, so of course there is a problem when I'm moving my index because I want my value to be before the 6, but it seems like I'm moving one line ahead, so the index is there. Index is 6, and I don't want it in the 6. I want it before the 6. So when this is 5, and when it's going to the 4, 5 is greater than 4. Yes, it moves to the next one. I don't want it into the next one. What I'm gonna do, I can create a previous index or or if I don't have a previous index, I need a previous index. If not, I don't need a previous index. I'm just gonna come here and say or control the move over here. If index next and index next val is lower than val, then I'm gonna move it. Not, I'm not gonna move it. Yeah, and then I gotta, of course. What's going on? What am I doing? I'm trying to get into the next val. Else. Infinite loop, of course, but interesting. Okay, I'm gonna if val if index next equals to move continue else I think that's probably no. I'm gonna use well, yeah, I think it looks like, yeah, if I play with the next and val, I think it's gonna be kind of risky even if I have this here, because I'm gonna end up working with multiple things here. So I'm gonna move the index till that place as I had it. And then I'm gonna move to head. I'm gonna move ref and prev next until it's not next index prev I want to move the next to the pref. And then finally move the index back to the pref. And there we go. We have the 5 in place. Now I'm curious about the 20. Yeah, it goes to the right place. What about a 0? Node 0. Yeah, there's an error in the 0 because index zero is greater than 0? No. So index stays in the same place. Previous is equal to head. Previous and previous is different index. No. So index is equal to previous. Previous is equal to head. So if index is equal to head, it should work. Again, 0 is greater than the 0. No, it's equal. So it breaks. Index is head. Previous, next. Different than the index. Yes. Yeah. So it goes everywhere. So, and index is not equal to head. And ta-da. Ta-da. It stays there. Now finally, to finish this, I'm gonna remove node int val strict node. If I'm gonna remove, I might change the element. I'm gonna do the case where one in the middle, just an example. Add node, remove node. So struct node asterisk index is equal to head for index not equal to val. That's it. If index, if it's valid, then let's see what we're gonna do. So we need int val. We need int val. Let's remove 14. 14th. If index, if it's valid, then let's see if it's head. If index equals to head, then we're going to remove the head. So head it's equals to index or to himself. Next. And since this is simple linked list, that's it. Else, if not the case, if it's in the middle, in the previous element of the head needs to point to the next one. So we need a pref. In this case, we're going to use something very similar to here. Or I want to move the pref to pref next, not the index. We're going to move the pref. So free, and that's the same. Index is equal to pref, and then well, not here yet. Else, we need the pref. We want to free. Well, actually, we can do free pref, but first we need the pref next is equals to index next, and then we can remove the pref, and that's it. If this is the last element, pref next, the index next is going to be null. I mean, it's going to be null, and the pref next is going to be null, and we can free. Oh no! See, if it is the very last element, if we're looking for, pref, but we're not going to free pref. We're going to free index. If not, we're going to get in trouble. Yeah, we just need pref to update the pointer. Okay, so let's see, remove 14 for yeah. Here we're missing semicolon. Oh. Okay, have a problem with it doesn't have a null. 14 is still there. Remove node. Here, print list. Let's just print it before. Okay. So we have 0, 0 to, okay. So the remove is not working in, the remove is probably working, but actually the 18 is getting, okay, yeah, this print is working, but the remove is getting to, okay. For index, well, I need to do something here, right? There it is, and the 14 is not there. That's it. That's how you work with single linked lists. And for now, I'm gonna leave it there. We did several operations such as create a list, print a list, add nodes in different positions, print it, of course, and remove and free, which is very important. Yeah, I'm gonna leave it there, and the next chapter is gonna be double linked lists. Hope it's helpful for you. Thanks.